In this recording, we're going to look at expected value and strategy in sports, specifically a couple of baseball questions. Okay, so question 33 refers you back to exercise 31. We're looking at a situation where we have a runner on first and we're considering whether we should steal second base and deciding if that is a good risk, okay, if the reward justifies the risk. Okay, and that's our question here. What's the minimum probability of success to make this a good risk, a good strategy? Well, question 31 refers back to an example in the chapter where we're looking at win probabilities at the end of a game. So what it says is, at the end of a game, you're thinking about what would be the probability of winning if we take this particular risk. And that's something you would do at the end of the game in the ninth inning. But it says earlier in the game, we would consider run expectancies to determine whether this is a good strategy. So something like, is stealing the base going to get me more runs, is basically a summary of this question. Okay, there's a lot of information here, and I find that when there's a lot of information, sometimes our eyes glaze over. Maybe we don't have a good sense of baseball, and it makes sense to make a diagram or an illustration of what's going on here. Okay, so what I would recommend we do is take this information and display it visually. Okay, so I've got 3 baseball diamonds here. Okay, on the left side, we've got the safe strategy. So what it says here is a team has a runner on first base, represent that with a dot, and no outs. Okay, with that situation, we can expect, on average, to get 0.866 runs. Another 6. Well, that's fine. We could stay there. No problem there. But if you want to be aggressive, and sometimes in sports or in business you want to be aggressive, you're going to take a risk. And with that risk comes the outcome of success or failure. Okay? If we are successful, we get a runner on second base. They stole second. 0 outs. And the expected amount of runs increases, right? We're up to 1.0857. Okay, it's like being a card player at the blackjack table. Do you want another card? Well, you might do better, but it comes at some risk. Okay, the risk of stealing the base or attempting to is that you may get thrown out. So now we have no runners and we have 1 out. And that doesn't leave us a very good expected value for runs, 2643. Okay, so all this is very complicated, but we've kind of laid it out visually for ourselves. So safe strategy, we could get this, or we could take a risk and get maybe a little better expected run value, or we could risk failing. Now it all depends on how likely the person is to steal the base, right? If we knew our runner would steal it 100% of the time, then you would send them every single time, right? Because you would get return on that. If they're not a good base stealer, then you're better off not. The question is, what's the minimum? How good do they need to be to make this a good risk? Okay, so we're going to make a good business decision here. So we've got our X, just like our probability distributions we saw before, and our P of X. And this is for the distribution of the risky strategy. Okay, so we know what the deal is for the safe strategy. It's just going to stay there. But this one has 2 outcomes. So the outcomes are we can get 1.0857 runs, or we can get 0.2643 runs. Now the probability is unknown here. So in math, when we have a probability that's unknown, we write it as a letter, right? Now the question is what goes over here, if that's P. So let me try to illustrate this. If you knew the probability was 0.7, this would be 0.3, right? Like what's left? If this were a 0.4, this would have to be a 0.6, right? Well, in each case, you're just subtracting from 1. So in this case, with our probability being P, it's 1 minus P. So whatever that is, this is 1 minus that. Okay, now we're going to be able to do our computation to figure out what's the minimum value of P to make this risk worthwhile. So we're going to do this comparison. Over here on the left side, this is our risky strategy, and we want that to be greater than the expected amount of runs if we play it safe. Otherwise, why take the risk? So, how we do this computation is just like we did before when we did our expected value. So we're going to multiply the value by the probability. So it's going to look like this, symbolically 1.0857p. We're going to add that to this product, 0.2643 times the quantity 1 minus p. And all that has to be greater than not the probability, but the expected value of playing it safe, 0.8666. And now we just need to do our solving, okay? Do some algebra here. So we distribute. Let's distribute here. So this takes you back to your algebra skills. You're going to distribute that and distribute that to the negative p. So we have minus 0.2643p greater than 0.8666. This is just solving it as if it were an equation. Next, we're going to combine like terms. We have two terms that have p's in them, and those add up to be 0.8214p. Okay, I just added this term, 1.0857p, to negative 0.2643p. Okay, now we're going to subtract this. Okay, and we've got 0. That looks like 6. Let me get rid of that. 0.8214p has to be greater than, on the right side we have 602, free. And finally, to isolate the p, we divide. Now p, as it works out, is 0.733. So what does that mean? Well, that is the probability of being success, remember? So in order for that to be a good strategy, a runner would need a probability of success of at least 73.3% in order to make this a good strategy. Our second example involves a person that's considering whether they should try to stretch a long hit and get a triple. Okay, so what I'd like you to do is read this description here. Okay, and having read that description, I would like, a triple means the person made it to third base. Okay, I'd like you to see if you can do a layout. Okay, can you set up your diagram, come up with your expected values, and can you set up your probability distribution for the expected runs of the risky strategy. So pause the recording now. Don't play it until you've gotten as far as you can with this calculation. Okay, so hopefully you took time to pause and work this out. If not, please do that now so you get the learning. Get as far as you can. Okay, so this is the layout I came up with. Okay, the safe strategy is we're staying on second base. We could probably make it to third, but we're not going to take that risk. Okay, we're not going to stretch this hit into a triple. And in that case, here's our expected runs. Now the risky strategy is we're going to go for third base. Okay, in that case, you get more runs because you're closer to home. Still no outs. The fail of that is you get thrown out at third base, and in which case you don't have any runners and a low run expectancy. Let's set up our distribution over here. The probability of distribution, again, p and 1 minus p, those are complements, and these are our two expected values. From here, if you have not done so yet, now that you've got all this information, see if you can set up and solve the inequality. Okay? Then play the recording. Okay, so here's your inequality. Risky and safe. Okay, the risky comes from combining these, multiplying and then adding these expected runs for the risky strategy, and our safe side is just what it was. So at this point, I would like you, I'd like you to pause the recording and solve this inequality for P, get as far as you can, and play the recording. Okay, so at this point, we're going to solve this inequality for P. So our first step is we're going to distribute. Next, we're going to combine our like terms, the terms that have P's. Then we're going to subtract to get all the numbers, the constants on the right, and the P's, the variables on the left. Now we're going to divide to get 1P. And so what I came up with was P has to be greater than 0.794. Now the question is, what does that mean? So write down your interpretation of that, your conclusion, and play the recording when you're done. So what you should have written is, a runner would need at least a 79.4% probability of success to make going for third a good strategy. Thanks for watching.